Our first speaker is, many of you know him. He's a graduate of Colorado State University, former colleague from there, though we never overlaid. No. Now he works for NOAA, so he's one of those great NOAA people. And he's got a great data set that I thought, if you don't know about it, that you should spend some time here to talk about. So without further ado, Andy Heidinger.
Thank you.
Give it up for
Andy.
Yes. And mics. Yes, I'm going to mic.
This is the mic.
Yes, you need to use this one or that one, or just talk really loud.
Well,
can you guys hear back there?
Yeah.
Okay. And by the way, if you hear buzzing, you should tell me. If you sit up here, you don't hear it. So hopefully the buzzing's gone, because somebody pointed out during the break. But if you would just raise your hand and said there's buzzing, we could have taken care of it right away. Or move down here.
Well said. Thank you. I'm Andy Heidinger. You guys all know me. I'm talking about, I guess, the data set that I've known and loved for a long time. And I want to make the point that this is really a CIMSS data set, the CIMSS resource. I want to make sure everyone here knows what it is. And I'll be showing slides from my other retronauts, Mike Foster and Andy Walter. But, hey, what is PATMOS-X? Steve asked me to talk about the AVHRR side, and it's really what it has been for its long history. But it is it's a satellite cloud data set. It's a climate data set focus from NOAA NESDIS, but it has a lot of work on CIMSS, and I'll say that's the CIMSS data set. We're mainly AVHRR. AVHRR goes back to the 70s. And so what we are expanding, if you're not growing, you're dying. So we're looking at GOES and MODIS, these PATMOS-X data set forms on these other sensors. We certainly want to continue on in the brand new years data set that should capture, show the real-time cool stuff. We are part, again, of the GeoX Cloud Assessment. Probably the meeting's been in Madison for 2 or 3 times. So many of you have been in that meeting. We were there. And we're a WMO Scope CM product. I need to point out, too, we're only one of many cloud climate data sets in our building. So I don't want to really want the first or last ones that think this. So the AVHRR, it's the advanced, very high resolution radiometer. And it was all those things in 1978 when it started. And it flies on the NOAA POSE satellites and still on Meta. So it'll probably run out of gas on Meta-C in around 2025. So that'll be almost 50 years of data. It's only got 5 channels, but they turn out to be pretty well selected, pretty well calibratable too. The set we're all familiar with here. And the global record's 4 kilometers, which isn't very high resolution, but it's been consistent over the whole period, and there is some 1 kilometer data. So, again, 1978 was the launch of the first AVHRR in tyrosine. You can characterize this with the birth of the first cordless phones. Here's Jack Nicklaus, these first phones. And the AVHRR was a 10-bit sensor with 4 channels and 4 kilometer resolution. And if you turn the clock forward in time, today, we have the last one up, the last, at least NOAA POSE up. And it looks exactly like almost tyrosine. But our phone technology has changed quite a bit in that time. Here's the Galaxy S3. Those that know, I'm a cutting edge cell phone user myself. But so the AVHRR, again, it's still the same 10-bit sensor from the 70s, 80s, 90s that come above. But now it's got 5 channels. So we've gained 1 channel. But the technology that's driven these cell phones has also driven other sensors like Calypso, MODIS, EASI. So we do have advanced sensors, so we can get a lot more out of AVHRR in 2013 than we could in 1978. So again, the motivation, why we're trying to use this sensor for climate records. I guess the obvious one is its longevity. With hers, the sounder it's next to the Palm Zone works with, it is the longest continuous, easily accessible satellite record. Its record is big enough, 30 terabytes, that until recently, was very much a challenging process. So all these advances, the ZAR and the PEATs, they really come into play. So we can do a lot more with this record now than we could in the 1990s. It turned out to be, again, it's a pretty good radiometer for all things considered. It's turned out to be very well calibratable. People are still publishing ways to get more out of it. And it doesn't do much, but it does use surface temperatures, cloud properties, aerosols, fires, vegetation, clouds. So that's a lot. And plus it's a NOAA NESDIS data source, so it's stars. So for a little history of the project, it does stem from the 90s. There was a big PATMOS-X project on the NOAA NESDIS funded under the Pathfinder program, which funded people to get ready for EOS. But actually, I was not really involved with that project at all, but I kind of stole the name, thinking I could get more money if I leveraged off that. So,
That worked.
it did. 2002, though, I did it a couple of years, so we started Collaboration in real time and then based PATMOS-X on that. Picked up a little bit of crucial funding from Mitch Goldberg to get this pilot studies, which kind of moved the data from NCPC to STAR and then to CIMSS. And then we got our first big break was a recalibration project by NCDC from 2009. So that was really our first significant money to do something with AVHRR. And we've since been funded by NCDC ever since to deliver that data and now to deliver cloud products. And more recently, we do have some money starting next year to do HERS work with the AVHRR that builds upon the long-standing work on this out. So things are looking very up for PATMOS-X. There have been times we had no money, but it's always kind of been a thread of our climate programs. So again, I'll just say something about algorithms. Again, the big CIMSS linking is we've taken a lot from the AVG. So as we've learned things under JPSS AVG here at CIMSS, we've stuck that right into PATMOS-X. In terms of ancillary data sets, we try very hard to stay current. When there's a new reanalysis, a new SST data set, we try to use it. But we do try to use things that have a 30-year record. So we don't maybe use the best snow data set, but we use one that's consistent over 30 years. We still use PFAS, Howell's model, with help from others. And we do use other algorithms traditionally from NESDIS. So solar insolation, OLR, surface temperature. So that's kind of our suite of products. The research that's going on, we've done a lot of work with Ralph Benard, some pollution impacts, cloud aerosol feedbacks. People have grabbed our data to do ocean productivity work with Chris Brown and now a gentleman who came in office. Of course, we do a lot of work with others in the long-term cloud trends, something that's we've been doing. A gentleman at NCDC does long-term aerosol. There's a University of Maryland fellow who does land surface temperature work with their data. And we work with NREL to do insulation climatologies. So these, again, we've never been funded to use PATMOS-X data, but these are the work that we kind of collaborate with others that grab our data and try to make scientific advancement. We do a little bit, of course. I think it's important that data providers also are their own customers, but this is kind of, so far, the current active projects we have. So what's on file? If you grab I'll show you how to grab our data. Our goal with our data has been to make something small enough to be useful, but it contains everything that we could think of that's people could use either to filter products in ways we didn't think possible, or to make their own data sets. About half of our business is people taking PATMOS-X products and making their own climate data records. So what we include all the radiances, all the calibrated brightness, temperature, and reflectances. We include things like radiance metrics, like standard deviations, and other kind of quirky diagnostics that people can use to filter when our cloud mask isn't always perfect. They can do their own cloud masking. We do a lot of ancillary data, things like reflectances and emissivities, so people can look and see if something looks squirrely in ancillary data. Very well might be a bad product to look at. We do include things like the NWP and RTM results for some channels, so again, so people can look and see if those look bad. You know, products are probably bad. We also do our standard cloud products that I didn't list, but if you're used to the Modus products that many of you work with in the building, they're very similar to those. We also do their uncertainties. We tend on optimal estimation, probabilistic cloud detection, so we always try to make uncertainties available in their products. And here's this, a picture of this, but again, observations, about a third of our data set is just purely level 1D observations. And here we have a standard deviation of the 11 micron in the upper right, sorry. Middle rows ancillary data are things that aren't cloud products, but things that we think are useful in the diagnostic. So that's about another third of our data set. And at the bottom row are the standard cloud products. Very similar to what you get from Modus. So we have mass type, pressure, and optimal depth. And about our total number is about 60 products in the PATMOS-X. To be or not to be? That's the question. So we've always been a very small project. So we've never had the space to store level 2 data. We've always struggled with how to give people data they want, knowing we can't store everything. So we've come up with just a purely sample data set that we call level 2B. It's in between level 2 and level 3. So and a lot of this is driven by Claudia student around in the UX cloud assessment, just trying to get her the data set she wanted the way she wanted it was very painful. So we basically did a necessity by throwing away 90% of the pixels and getting something that's flexible so we can participate in the next UX cloud assessment. So we probably should have called it level 2G, as Steve has said many times, but we did. And basically, he's going to just, Nadia gave a very nice talk about her space-time grading. And this is kind of even more simple than that, but we just basically snap to a grid, if you will. We throw away, take the nearest neighbor, we throw away 90% of the pixels, I think, for AVHRR level 2B. So we keep a 0.1 degree resolution data set. But we lose many pixels, but we have the total flexibility to do what we want to do, the data set and users. So we find this to be very, very useful. And things that we do with this level 2B data, we still can do our calibration. Here's a level 2B global image you would get from the website. We do pixel by pixel comparisons against Modus, the Modus level 2B data we make. We make level 3 from level 2B. And we also do these arbitrary n-dimensional histograms. So here again, I show one that the ISCIT makes, and these are in the Modus data set too, the level 3. But we have the choice of doing any of these 60 parameters against any other of the 60 parameters. So it's worked out very well for us, and we've been able to, as I said, we've had a lot of applications I never thought of, like these ocean productivity, and the data sets seem to work well because people have the information they need. So another thing I want to point out too on the level 2B applications is another benefit is that we maintain the pixel positions relative to each other. It's really a sample level 2 data set. So you can do things like shown here. Here I'm following a hurricane. There's nothing easier to track than a hurricane. On the left is the 11 micron brightness temperature from PATMOS-X. In the middle is the CFSR reanalysis, one of those ancillary data sets we keep. You can see a little pressure. And on the right would be just kind of like an object analysis where I picked out the deep convection in white gray is one object, and the white areas are where the convection is hitting the tropopause. So, not that this is a profound result at all, but this is the kind of stuff that you can do with level 2B, and it's stuff we work on with other people to do this kind of work. So some of the analysis that we do, I'm going to show now the AVHRR. Again, one of the things you notice with the AVHRR, that there's a lot of data missing early on in the years. So we're constantly trying to increase our yield. The gray would be the theoretical yield. Every data set from every AVHRR was available to us. It's never the case. So we're often talking to Europeans trying to get more and more of these gaps filled, especially early on in the morning satellites. But now you can see we have up to 8 per day. So it's been kind of a neat sampling exercises. Here from Mike Foster is the solar time of every satellite. So you can see it's kind of a chaotic mess. The AVHRR. There's both a blessing and a curse. So while the orbit times aren't flat, meaning they're not horizontal lines as they would be in MODIS, you do see every part of the Earth at every hour of the day over 30 years. So this paper just came out. It's a nice study by Mike Foster. You can take that information and you can derive the Dyna cycles. So here is hottiness for January and June. The red symbols peak in the morning, the blue ones peak in the PM, and the arrows, they point to the hour of the day where the peak is, and the size of the arrow is the magnitude of the Dyna cycle. So this is just a nice way to get more information from your data set. Of course, we have geostationary results, and these can be used to confirm this, but our geostationary record still really doesn't go back long enough to make this not relevant. So this is important. Any time series you make from the AVHRR has to be corrected for these effects. So I'm going to show one current thing that we're working on. Is George Roaring asked us to write a North American climatology, or contribute to a North American climate chapter. So we looked at cloud properties. Here is the mean trends by season for PATMOS-X level 2B over the AVHRR record the last 30 years, from winter, spring, summer, and fall. And the trends basically, red is 5%, dark blue is -5%. So we do see some trends for this, regionally short amount of time, which is not too unexpected. But the question is, how do you believe this? You have to believe this. You have to believe our Dyna correction. You have to believe our calibration is consistent. There's 14 different sensors that go into this, so it's always the issue with our record. So here's some of the stuff that we do. Here is a time series at the top of all the different sensors that contribute to this, and sometimes there are more than one. So that's our record for one of these areas. The middle is the difference when there's one or more sensors, the difference between the two at the same time. So it gives you a sense of is there a systematic difference in any one of these sensors? Is there a trend in the difference that would indicate something's very wrong in your algorithm? We don't necessarily see that here. And the bottom is in fact our trend. So corrected for both diurnal effects and having looked at these sensor-to-sensor differences. And the gray area is our estimate of error. Is that right, Mike? So another thing you can say is, well, okay, it seems to look okay from a sensor-to-sensor interconsistency. But then you can bring in things like other data sets. And right now we're looking at the ERA reanalysis, which doesn't actually use AVHRR, but does use some satellite data. So you can see here at this top curve, the black is the satellite PATMOS-X, the gray is the interim reanalysis, analyzed the same way over the same region. You can see there's bias, and that's okay, as expected. But the important thing is that the blips follow each other very well. So, this fact or fiction debate, it doesn't appear that our interannual variability is false or derived from, say, bad calibrations or bad insular data. So, this is the kind of work that we're doing to try to really get to the bottom of these 30 years records are really robust at all. And we also have a study going on that I didn't show with Melissa Freed, who's doing similar work comparing PATMOS-X surface-based measurements of Clytus from the various VSOS and weather odds. She's done a lot of work tying that together. It's a story in its own, but it also shows kind of a nice correspondence in year-to-year variation. So again, I don't know what the final story is with this, but we're trying to unravel all the possible sources of concern. Go ahead. Okay, so I do, again, I'm trying to make the point that this really is a CIMSS resource. About 10 CIMSS people have worked on this project over the last 10 years, so we do have a kind of an embarrassingly simple data portal, but the AVHRR data is served by NCDC, so I think that's the global data, they should be the place to go for that. But we do serve some in CIMSS, and for example, here is, we serve the AVHRR global data, but for a short time. We do some sub-regions. We have the USA, the Great Lakes, and the North Pacific. So there's small boxes that you can grab very, very easily. I can do work on my laptop. It's really the North Pacific. Goes east and west domains. Those are for shorter times. And we do have 1-year MODIS areas in 2010. So we have a Perl script that you can grab the data, or just go to do an FTP source. Again, NCDC is the global level 2B data provider, and they have really cool tools. And the GeoX assessment is available now publicly, so you can grab PATMOS-X data in the same format you can grab ISKIP or HERS or I think a dozen or so other data sets. So it's a nice new available thing. We are working on a new multi-project data portal though, so please give us comments on what you would want to do with the climate data source. Because that really is one of the big, I think, limitations of climate data. It's easy to make accurate products, not easy, but it's possible. But getting the data in a way to serve the special needs of the climate users is a challenge. So yeah, I want to acknowledge we've had a lot of CIMSS people, CIMSS and NOAA people work on this project for over the years. So it's been, again, we've been a very small project, and we've really leveraged our very creative people that have added to this and continue to do so. The key, of course, what really got our ball rolling was making that 2010 delivery, which we never would have done without Steve Dutcher and Liam and the team. So thank you. The Zara cluster now is really a game changer for us, able to do these big processes on our own and experiment with the data sets. And of course, be remiss in the long NOAA foundation of guys like Mike Weinreb, Jerry Sullivan, all the work we do, Larry Stowe, all the work we did there. So where to go from here? I think there's a couple things I want to say. This interface is critical. I say this because I'll never be able to do it on my own. And it is, I think, the climate community is mainly researchers at universities who have very specific questions, often little patience, and they want it the way they want it quickly. And so I think I know we lose customers in the PATMOS-X realm because we can't give them the data the way they want it. I'll point out this AVHRR and HERS work. We got some additional money now to carry on the work that we've been doing with Holland's out. And there's really, I think, a great benefit of AVHRR and HERS. You can make a MODIS-like data set, I would say. You can think of these bands 0.65, 3.867, 8.5, 12, and 13.3 as a foundational data set. That AVHRR and HERS will take you back to 78, Chris and Burrs in the future, and the ABI will give that to you. The global GEO will have that soon too. So I think there's a big debate in the climate community. Does every cloud product have to look like AVHRR? That would be bad. I think this would be certainly a useful data set for us. And also, there's much more European activity in this area than American. So I think we as American scientists and NOAA, we need to partner with them, but would also think we need to focus on areas where we can be leaders. repels, for instance. So that's just the funding reality. American funding is down, but most of this data is American data, and the Europeans tend to be more aggressive with, so certainly the cloud planning community pushing forward on these things. I think that's it. Yeah, so I'll have this nice graphic we had to make for NCDC for our website. So, thank you.
Thank you. Any questions? So, turn on the lights. Questions? Comments? Yeah.
So you are still looking for AVHRR data from the past?
Yeah, we are. There's for the morning orbiters of the AVHRR1 series, NCDC had a tape failure. So there are still some big gaps for NOAA-6, 8, and TIROSEN 2.
Yeah.
For your cloud trends, what's a cloud?
What
I know
say
it when I
is,
see one.
yeah, that's a tough one, George. Yeah, thank you for answering.
Give me my answer. I know one when I see one.
Yeah, well, it's kind of the answer. You know when the sensor you're looking at sees one. And we know that we're about a 0.3 optical depth sensitivity and greater. But you're right, you would get a different answer from a microwave sensor, most likely. You could get a different answer from a sounder, and all those things could be the right answer. But, so you're right, no one can, the cloud trend is only pursuant to the, to the subset of clouds that your sensor is sensing.
So those trends you were showing, given the uncertainty in the gray bar with it, were those trends significant?
Yeah, right. I'll Mike answer that.
Yeah, there's a little N star, so yeah, there's more work to be done, but according to the statistical test,
Yeah.
looking at how long it would take for those trends to be considered statistically significant, we're getting numbers between about 20 and 25 years in terms of wired length of the vector, and we're up to 30 years, so the idea is we're just about at that time where we're maybe able to say something.
So, but are they statistically significant? Given that they can be, are they?
Those right there are based on that test first.
Well, okay. Other questions? It's a great data set. I was invited to give a talk at CSU's 50th anniversary. They called back some former students, and so I talked about an energy budget study I did back in 1979, and I used the TIROSEN to derive cloud amounts. And I had these pictures, and I went to Andy and said, back in 1979, 1980, we were doing things a lot different than we're doing now. And so I asked him to generate it for that region with his current data set. And he did 1979, and the entire record in, how long did it take you?
Not much, because the ZAR cluster is a game changer. But yeah, a couple days.
A couple of days. It took me over 2 years. Question up there? Okay.
Yeah, just what format is all that data in?
That's a good question. HDF is what we serve on our website. NetCDF is what NCDC serves. And we do intend to serve NetCDF data, but HDF is what you'll get in-house.
For